Actually, I'm going to do the following. Let's pick a strike. 80. Current. 68.50. Percent out of money. 80 divided by 68.50 minus 1. Okay. So that's 16% out of the money. Divide that amount by the period volatility. Basically, $80 is 1.07 standard deviations above the current price. Now, using normality assumption, I can figure out the probability that it's going to end up over that. Norm S test. Got 1 minus. Norm S test. Where are we? So probable that this option is going to end up in the money is 13%, which is not small. This is 2 weeks. Now, suppose using the same prices, we were talking about Coke. Okay. Again, let's say Coke is trading at 68.50. We're looking at an 80 call. Given that Coke has that 21% annual volatility, what are the chances that this 80 call is going to finish in the money? Practically nothing. Okay, let's be a little bit more reasonable. Most individual stocks, larger ones, are around 30%. So if you reduce the volatility by half, you reduce the chances of finishing in the money from about 14% to below 2. So if I gave you a choice between these two options, and I said, I'm going to charge you exactly the same price, which one would you pick? 80 call on Uber, or 80 call on Coke, whatever that is? You're going to pay the exact same price. Uber, because the chances that you're going to make money out of that is much higher. If 2 things cost the same, but one of them has a higher chance of making money, you're going to pick that one. One of the basic rules of statistical arbitrage. That's why the higher is the volatility, the higher the option prices. For example, Palantir is going to announce their earnings today. Typically, the day before earnings announcement, or if it's after market close, the day of the earnings announcement, those implied volatilities go berserk. Let's go to my retirement thing. I have a 17 put that expires this Friday. They paid me $1. So then I sold them, $1 per share. I have 2 of them, so I got 200. Look at the implied volatility, 163.62. Okay. A week ago, that volatility was 100%. The chances of something possibly going wrong that day is a lot higher. On the other hand, remember, this is the same company. I own long-term options, 37 calls that are due January 2026. And I paid about, this doesn't reflect the whole thing, about 180. So I'm making money now, but let's look at the implied volatility, only 58%. This is still pretty high, but remember, this is a relatively small is a relatively tech company. So things could go up. But it is not 162. In fact, when I bought these options, I think the implied walls were around 51 or so. So the lower the implied walls, the cheaper is the option. So you got to pay attention to those. Now, ideally, I would have talked about some math, Ito's lemma and stuff, but I'm just going to write down kind of a formula under a specific condition for a specific type of option problem. But that's going to be kind of the cornerstone of a lot of things we're going to do. This is called the yes. Black-Scholes formula for European options on non-dividend paying stocks. Assumptions. A. Volatility is constant during the life of the option. There is almost instantaneous trading ability. And assume that there are no bid offer spreads. So if you want to buy or sell anything at a given price, you have no problem doing that. Interest rates are constant. During the life of the option. And stock returns follow a so-called geometric Brownian motion. Which is a geometric version of it's named after a Scottish botanist named James Brown, I think James, but the person who actually made anything with that was Albert Einstein. He used that in his photoelectric effect paper, I think, the one for which he got the Nobel Prize. And that also kind of laid the foundations for the quantum theory, but they never gave him a Nobel Prize for relativity. There's nothing that says you cannot get 2 Nobel Prizes. But they kind of had to give it to him. But remember, he got it in 1921. He's in Germany. A lot of the Nobel Committee are German because Germans were big in theoretical physics. But also remember, this is after the First World War. Germany is in shambles, and guess who they blame? The Jews. Not only is it the Jews, but it's also a Jew that was born in Switzerland. And they didn't want to give him a Nobel Prize for his real accomplishment. But they also knew they had to give him one. They gave it for that. This basically says some sort of mean numbers times dt sigma dz. Now, I use dt instead of a delta t. In mathematical notation, we use delta for discrete changes, dt is for kind of a continuous. If you remember, if you took calculus, you write changes and calculus as d, not as deltas. Deltas are actually discrete changes. Anyway, this assumes that everything happens in continuous time, all right? It makes the math easier, that's why. Other than that, it doesn't matter. dt is basically an instant. Have you guys ever heard of the term infinitesimal? It was probably invented by either a German or a Norwegian guy. It's basically a bastardization of infinitesimal. And infinitesimal is a positive number that's small, that's less than any other positive number. It's kind of the other way of thinking about infinity. How do you define infinity? It's a number that's bigger than any other number. It's kind of circular, but that's the way mathematicians think about stuff. So dt is an instant. And dst is change in stock price at this very moment or instant. And mu is some sort of what we call drift. If mu is 5%, that means if nothing changed and the dz stuff was 0, over a year you would have made 5%. This change divided by the current price is percentage change, right? This dz thing is funny. This is known as the Brownian increment. It's a random shock to the system that came on that very instant. Okay? And dz is assumed to have a normal distribution with a mean of 0 and a standard deviation of square root of delta t. Okay? Or variance of what you want to call dt. I still call it dt. I wrote this down not because math is any interesting,